Now that you know a little bit about differential equations and how to solve them, we're going to start getting into the applications. And one of those first applications is exponential growth and decay. At the end of this lesson, you'll be able to write and solve a differential equation to model growth or decay. All right. When we are solving exponential growth and decay problems, we will be relying on using the law of exponential change, which states that the differential equation that describes growth is dy dt equals ky, where k is the exponential growth constant if positive, or exponential decay constant if negative. Alrighty, let's take a look at example 1. In some chemical reactions, the rate at which the amount of a substance changes with time is proportional to the amount present. So I could write a differential equation due to that. However, this example nicely gave me what that would. For the change of gluconolactone into gluconic acid, for example, this would be the differential equation that goes with it, where T is measured in hours. And then here would be the example. If there are 100 grams of this gluconolactone present when T equals 0, how many grams will be left after the first hour? So what we need to do, we know how fast the level of the amount of substance is changing, but what we need to do is find out how much would there be, or how many grams would there be. So what we're going to be doing is solving this differential equation. So I'm going to go ahead and write it down. dy dt is equal to negative 0.6y. I'm going to put a 1 underneath, cross multiply, so I'll get 1 dy is equal to negative 0.6y dt. I need my y's on the same side, so I'm just going to divide by y. We're not going to do anything with the negative 0.6. So I'm now going to have dy over y equals negative 0.6 dt. I'm ready to take the integral both sides. The integral of dy over y is the natural log of y. And then the integral of negative 0.6 would just be negative 0.6t plus c. Again, we could just do my logarithm loop here. So I'll get e to the negative 0.6t plus c is equal to y. And again, we know that we can write the c out front. So I get y equals ce to the negative 0.6t. That will give me how many grams are present after any number of hours that they give me. And this specific formula says how many grams will be left after the first hour. So we're going to let t equals 1. Well, actually, we can't do that yet because you'll notice I do not know what c is. So I am going to use what they told me. They told me that there are 100 grams, so y would be 100 when t equals 0. So 100 equals ce to the negative 0.6 times 0. Negative 0.6 times 0 is 0. E to the 0 is 1, which means c equals 100. So I'm going to have y equals 100 e to the negative 0.6t. Now I can use that equation to figure out how many grams will be left after the first hour. So to figure that out, you can just plug 1 in for my t. And if I get out my calculator and figure that out, there would be 54.881 grams of the substance remaining. So hopefully now you're somewhat familiar with solving a differential equation where there's an application involved.